Hello. Good afternoon. Happy New Year, Gavin, Graham. Good to
Happy
see
New Year,
you.
Marisa.
So it looks like you guys are at the North Pole. You know, it's January 5th, right? Like I didn't know you were the type to like hold on to the holidays this far after.
Well, we were really seized by the spirit, and we went to the North Pole, and we kind of realized something when we got here, Gavin.
Yeah, there's actually no landmass in the North Pole. All we found was a bunch of sea ice.
No like workshops and toy
Not
making
well,
or-
not that we can see. Right here, we've got a little bit of open water, as you can see behind us. And so we thought, since we were up here, we were seeing some of the magic of sea ice at work, that we might talk about sea ice today.
Yeah. And I mean, you're not really in the North Pole, though, right? Like, Graham, where are you right now?
I'm in New Hampshire right now.
Is it cold in New Hampshire?
It is cold. We actually got a little bit of snow this morning. I'm pretty far away from the ocean, so I can't find any sea ice from here. But I also heard it's pretty chilly out in Santa Cruz today.
Oh my goodness, we might see sea ice and cowls if we keep going at this
It has
rate.
been
It is
chilly.
freezing.
It's true.
But
It's true. Well, I'm excited to talk about seasonal changes of sea ice with you all today. So, and for those of you joining us on Facebook, if you have any questions along the way, drop them in the comments. And at the end, we do have a rock that we're going to have Gavin and Graham ID that was sent in, and you are also welcome to send in your rock pictures for us to ID. You can email them to events@santacruzmuseum.org and take it away, gents.
Thank you. All right. So sea ice. Gavin, so let's start with just like a decent overview of sea ice, and then we'll help to contextualize it on Earth. So
yeah, that sounds good. And Graham, maybe before we jump into what it actually is, we should introduce these two pictures, right? So
yeah,
on the right, I recognize Antarctica. We've shown that in several pop-ups now. This is the continent of Antarctica as it looks in the summer. And then what about the left, Graham?
yeah, over here on the left, you can see that same outline of Antarctica in here. But then there's this whole apron of, not quite so bright white, a little bit of blue under there, and that's sea ice. And so Antarctica, you expand it dramatically, but you don't expand the land. You're just extending this ice cover way out. And I think that's one of the key takeaways of kind of thinking about sea ice, is how it can sort of build off of things. So let's help to understand why we see those differences in those colors between the interior ice sheet and the sea ice.
Yeah, Graham, I think that the best place to start is just to look at the cryosphere as a whole, and we'll define cryosphere in a second, but look at all the ice on the Earth's surface as a whole and see how sea ice fits in. And then we'll get into how sea ice forms and stuff. But I think this is a good starting point. So Graham, what is the cryosphere and what does it make up?
Yeah. And this is a really key question, because the cryosphere is many things. In the exact sort of definition of the word, it's all the frozen water on Earth's surface. Cryo meaning ice and sphere meaning the globe. So it's all the frozen ice on Earth's surface. So that's things like glaciers and ice sheets. It's the snow on the ground. It's permafrost that's frozen into soil. And so it's this whole broad range of things. But to sort of help make sense of sea ice relative to the major ice reservoirs on Earth, let's talk a little bit about what glaciers are and ice sheets and how those kind of fit into the cryosphere.
Yeah, sure. So I like to start with ice sheets because we study them. We've talked about them a lot. And so ice sheets are giant masses of ice that cover whole continents, right? So there are two major ice sheets on the planet. There's the Greenland ice sheet, which you show down here on the bottom right, and then there's the Antarctic ice sheet, which we showed before. So two major ice sheets where ice is covering the full continent. But Graham, what happens when the ice kind of spills over off the continent into the ocean? What do we call that?
Yeah, so at the edge of ice sheets, or even sometimes at the edge of ice caps, which don't cover the whole continent but cover parts of them, when those large bodies of ice hit the water, um, they'll start to actually float off little portions of them. So here we've got the grounding line. That's where the grounded land ice makes it out into the sea. And then it starts to peel away and floats off in an ice shelf. And now that ice shelf is still attached to the glacier or the ice sheet or ice cap. But then as you can get to the edge of these things, that ice shelf becomes weakened and parts of it start to break off. And those big chunks of ice that we release into the ocean are called icebergs. And so are icebergs sea ice, Gavin?
Very good question, Graham. They are not sea ice. Icebergs are not sea ice. And the reason that icebergs are not sea ice and mountain glaciers are not sea ice and even permafrost, like you see on the top right, the difference between all of those parts of the cryosphere and sea ice is that sea ice actually forms in or on the water. Correct, Graham?
That's right. Yeah. So these glaciers and ice sheets, these all start out as snow and they work their way across land and into the water. And although snow can play a role with sea ice is always starting forming out on the ocean. And so before we go into that formation mechanism, though, let's first think about how sea ice just changes normally.
Yeah. So as we alluded to, there's a huge seasonal change in both Arctic and Antarctic sea ice, and we'll talk about the Arctic in this slide. So, Graham, in the summer, you have pretty much no sea ice. It's too hot. It melts.
That's right. It melts down to this really reduced state. Oh, sorry. Go ahead, Gavin.
Yeah. I appreciate that qualification. It doesn't all melt away. It reduces drastically. Correct.
That's right. Yeah.
And then in the winter, just months later, same year, months later, it grows dramatically.
Yeah. And you'll see in here that when the sea ice in Antarctica is at its largest and in the Arctic are at its largest, those are flip-flopped relative to each other because they're opposite hemispheres. We've got winter in the northern hemisphere, it's summer in the southern hemisphere. But like we were talking about there, Gavin, right, not all the sea ice goes away in the summertime. And this is something that you can see here in this reconstruction of sea ice in the Arctic over the last 30 some years, where the really bright white is old ice and all the paler blue is young ice that's forming newly that year. So you can see that there is some sea ice turnover, but through every seasonal cycle, it grows out and shrinks back in.
So neat, Graham. Look at that. Yeah, I wonder that could be some, sea ice that's 10 plus years old in there.
Exactly. It can get really ancient. And so I think this kind of prompts the question for us: what makes some sea ice last for years and years, 10 years or more? And what makes some of it just last for, the one season before melting away?
Oh, great question, Graham. Got to talk about the formation mechanisms and what it looks like.
That's right. So we'll cut this video short. But first we'll also take a look at the Antarctic sea ice and appreciate how it's changing there. I forgot about this slide. Sorry, G.
That's right. I threw this one in there because I just love Antarctica so much. And this is unbelievable. So at its peak in the winter, Antarctic sea ice covers 6.6 to 7.7 million square kilometers. So that's an area roughly double the area of the US. So it starts off, it is starting off in the peak winter as just this massive of sea ice. And then it melts down to, just a fraction of that in the summertime. So this is a really, really drastic change throughout the year in the cryosphere.
Yeah, that's incredible. And it's cool to see this, this counterpoint video showing how it can sort of gradually grow out there rather than the rapid one. So cool. So we see it grow out there, but then how does it grow? So sea ice has to start in open water. It's going to form, it's essentially forming snowflakey like sort of things. It starts from a nucleation point and it grows out from that point with the start of the crystal. And when we first start to freeze ice over water, it's called frazzle or grease ice is the common word for it on the ocean. I think because it's supposed to look a little greasy because it's still slushy. It's not really coherent. It's just this thinnest little bit of ice that's sort of, adding this slushy layer to the top of the ocean. But as that starts to solidify, Gavin, what can happen to it?
Yeah, so it's basically like morphing together and starts to like finger out and raft, and you get this rafted ice. That's kind of, this is a close up picture of what's happening, on a, continent wide scale in the last movie. You have this ice starting to form, it's crystallizing, it's going to this grease ice, and then it's really sort of coalescing and starting to raft on the surface of the ocean.
Yeah, that's exactly right. And in this grease ice phase, right, we're just forming those crystals there. But then when we start rafting things and we start putting layers of ice over one another, this is when we start adding in another component. And this is the component of wind. And wind is going to help to play a role to move these masses of ice around to interact with one another. That will ultimately help to thicken them. So if finger rafting goes on long enough, we get layers upon more layers. We get these neelas, which is finally where we get ice that's usually strong enough to not be really broken up by the wind. And as we keep sort of crunching these together, overlaying them, and adding sheets and sheets together, we get what becomes young ice. And if it lasts the whole year long, then we start to talk about ice flows. And we've got two flavors of ice flows, Gavin. What are those?
Well, I think that you're talking about first year sea ice and multi-year sea ice, correct?
That is indeed.
The two flavors. So I'd imagine, I actually am not familiar with these, Graham. You'll have to remind me, but first year sea ice is sort of the first year after these neelas form. Is that, or this young ice forms?
Yeah, and so first year sea ice will just be the sea ice that just lasts 1 year. But if it gets thick enough and stays cold enough to last multiple years, that's when we get to this, this really impressive multi-year sea ice that you were saying can last, a decade or longer. And one of the things that helps it is, right, you get these, this overlayering of these rafts that sort of slowly build up into thicker flows. If they get a little snow on top of them, that can help to insulate them and keep them lasting from year to year. And then what's really cool is that all of a sudden, these large sea ice flows can start to crash into each other and build pressure ridges. And for folks who have tuned into the Rockin Pop-Up before, these pressure ridges are a really familiar process.
Yeah, Graham, it's so interesting. I love this analog you have here, where you have a continent collision. Think about, we've talked about this before, but think about the Himalayas, where the Indian continent crashed into the Eurasian continent, and basically you get this over thickening of the crust there, and this is exactly what's happening in these basically sea ice mountain ranges. So Graham, this is not just like icing over a pond. Sea ice is much more complicated than this. Very, very interesting, where you get this like first year sea ice where it starts to ice over after you've like had the finger rafted stuff. But then if that starts to really last longer than a year, you get these big consolidated layers and these big pileups, basically, right?
Yeah, and these things can be taller than a person. This is a pressure ridge, and these sort of ice rubble piles. They can be very typically this large or even larger, and you can see these great sort of sutures across sea ice flows where they've crashed together and formed these pressure ridges.
So neat.
Yeah, but sea ice isn't only getting thicker and taller. Sometimes those same winds that drive them together and thicken them can also help to open them up.
Yeah. Yeah, go ahead.
Yeah. Oh no. No, you go ahead, G. Sorry.
No. So you're introducing these openings in sea ice. So you get these big platforms. Very generally, you get these big platforms of sea ice, but it's not always continuous, right? So we have two flavors. I like this. This is a theme of two flavors of openings in sea ice. The first, I like this picture here on the left. Leads are where new ice forms. So that's basically, as you're moving the ice, you open up and you could form new sea ice in there, correct?
That's right. Yeah, you open up these little pockets, and this is just how you make more sea ice. And so this is usually related to wind and currents moving the ice around. You open little bits up, it's still plenty cold, and it ices over. But sometimes there are places where ice never forms. And what do we call those, Gavin?
Well, this, Graham, is called a polynya. Great word, polynya. But they're big holes in the sea ice, and ice either has melted from there or never forms there at all.
Yeah. And so I love what you've put in here. You've got this, this great sort of image of one way in which polynyas form. So take us through.
Yeah, so polynyas are really important in Antarctic sea ice. Just a real quick aside, Antarctic sea ice is a little bit different from Arctic sea ice because the Arctic is landlocked, whereas the Antarctic sea ice forms in the Southern Ocean and just kind of forms out into the ocean. There's no land mass around there. And so Antarctic sea ice is really controlled by the ocean around it. And as you might have heard us talk in terms of the Southern Ocean previously, there's a lot of upwelling zones and complexity in terms of the currents around the Southern Ocean. And oftentimes in these upwelling zones around the Antarctic, you bring warm ocean waters up to the surface. And when those warm ocean waters contact the base of the sea ice, they can open up these massive holes called Antarctic polynyas.
Beautiful. Yeah. And so with all of these processes, right, we've got this whole zoo or menagerie of the different ways that sea ice can behave. So we've got, our leads where things first start to form out of, you start with fractures that are driven by winds and currents. Ice forms in the leads. The flows thicken and grow pressure ridges. There are places that are drift or pack ice, and then places that are stuck onto the shore and land called fast ice. And so there's just so many wonderful things going on that makes this just a delightfully complicated Earth system environment.
Yeah, it's pretty cool. And you can see them all in action in the top left picture of Antarctica. Pretty neat.
Gosh. Antarctic sea ice, it's got it all, right?
Told you Antarctica is more important than the Arctic, Graham.
Ooh, Gavin, those are fighting words. But we'll save that for after the pop-up. And so we talked about that sea ice or the land-fast ice, and land-fast sea ice is super important in especially Arctic, but also probably some, a few Antarctic environments where you do have land exposed at the coast. Because this ice can protect the shore. And when you start to have, lesser land-fast ice, that can really drive a lot of coastal erosion.
Yeah, Graham, I'm glad that we're getting into this now, because folks at home might be watching this and say like, okay, guys, you're talking about the sea ice and it's really interesting how it forms and stuff, but is there like any, broader implications of this? And it turns out there are lots of broader implications. One being this one you've brought up. So especially in the Arctic, where you have a bunch of landmass around it, you have sea ice buffering you from erosion. And in Antarctica, where you just have the continent around it, sea ice is actually buffering the continental ice sheet from basically eroding away. So sea ice in the winters, especially in Antarctica, acts to hold all of the ice into the continent and buttresses it, kind of holds it back from flowing a little bit. So
yeah, so it's that sea ice, it's wee but mighty compared to those ice shelves.
That's right.
Cool. And so we talked a little bit about how sea ice forms, but then there's this really fascinating side effect of freezing out sea ice, Gavin. And what's that?
Yeah, so sea ice also forms brines. So brines being very, very salty water or salty fluids. And the reason this happens is because when sea ice forms, it basically takes the ice crystals take up all the water molecules, but they leave behind all the salt molecules that don't fit in the ice crystal lattice. And I like this picture here on the left because you can really see this process in action. So you can think about the pink as all of the salty water that is being stuck in the ice, but is not actually going into the ice crystals. So that's why you see this very, very clear ice around the sides, but the pink is kind of in pockets by itself. It's not actually within the ice. And so this is called basically brine formation. And it happens on a really large scale when sea ice forms. And eventually that brine that's stuck in the sea ice but is not actually in the ice crystals itself makes its way to the water below it. And so there's a really, really neat video from the BBC. I didn't put it in, but here's a snapshot from it. And this is basically a brine sickle. That what happens is that these brines kind of coalesce into pockets within the sea ice. And when they get close enough to the water, they break through and they basically fast freeze as they get into the ocean below it. So this big spout here that's making this big frozen path as it goes is brine being excluded from the sea ice. Now, we're going to go into the implications of this brine in a second, but the first implication is that this brine is a really important basically place where nutrients and microorganisms form and thrive. So these brines have all of these, or sea ice has all these brine pockets. They're filled with nutrients, and that has implications for the biology of these systems. But Graham, is there any other implications for these brines that we should get into?
Yeah, well, so these brines are forming these salty layers right below the sea ice, right? This is the part of that won't go into the ice above it. And so you're leaving these really salty layers of brines either beneath the sea ice or out at the margins of sea ice. And one thing we've talked about before is the importance of cold, super salty water in the North Atlantic for driving these deep ocean circulation processes. And so the sea ice, and when sea ice gets out to these really advanced positions, this becomes crucial for helping to drive the ocean conveyor belt or deep ocean circulation.
That's right, Graham. So this brine formation isn't just in these tiny little pockets like we show on the top left. When you get a large enough ice sheet, you can get lots and lots of brine forming under the sea ice. And that actually, as you said, drives ocean circulation in a way because it drives the ocean conveyor belt, which we talked about in the previous pop-up, where in the North Atlantic, all of this brine sinks to the bottom and it forms North Atlantic deep water. And that is driven around the global oceans by this conveyor belt, which we show here on the bottom right. So now we're talking about sea ice as being a really, really important facilitator to ocean circulation, which in itself affects climate and all kinds of global processes. So sea ice is a major player here. Pretty cool.
It does, yeah. And it's not the only thing driving ocean circulation, but helps to really set that stage for salting and cooling off, these northern waters that drive it. And so, we often think about sea ice then when we think about how climate is changing, but this is an important distinction to make when we think about how sea levels are going to change in a climate, in a warmer climate that will likely, host less ice. And so the key thing here when we talk about sea ice is because sea ice is already floating. Gavin, if we melt sea ice, will it significantly change our ocean depth or our ocean levels?
Yeah, it turns out it won't, Graham. So sea ice melting and refreezing doesn't actually affect sea level very much. When we think about what affects sea level, that's when we're talking about the ice sheets melting and the ice caps melting.
That's right. And the key thing here is that, right, when we're freezing sea ice, we're not really pulling water out of the ocean. We're just floating it up on top of the ocean. But when we start losing ice off of the land, we're putting new ice that wasn't in the ocean before into the ocean, and that's going to drive that higher sea level. And so an important distinction to make, but that doesn't mean sea ice is not going to play a role in our changing climate. So Gavin, what's happening to sea ice in the Arctic over the last, several decades?
Yeah, when you think about the maxima, so when we look at the maximum extents of sea ice in the Arctic, this is happening in the winters. And what's happening is that as global climate is changing and getting warmer, the maximum amount of sea ice in the winters is lower now than it was decades before. So we're getting less sea ice in the winters, and the same thing in the summers. We're getting less sea ice preserved in the summers, right, Graham?
That's right. And we're seeing this sort of long-term decrease in the multi-year sea ice, these strong, thick layers of sea ice that play not only a role, well, that play a large role in where we have places of open water, and those help to drive really important processes that allow life to survive, and for humans who depend on those life as food sources or other resources to be able to have access to those. And so sea ice is this crucial part of Arctic ecosystems. And as it is changing, as our sea ice maxima and minima are shrinking on average over the course of time with climate change, that has really important implications for those ecosystems. But Gavin, as you've mentioned a couple times before, sea ice also has a really important climate feedback as well.
That's right. That's right. So sea ice, I was thinking that you're referring to the ocean circulation, but actually sea ice also affects the temperature of the surface of the Earth, Graham, because if you imagine when you have your maximum extent of sea ice, it's covering the Arctic Ocean, right? That is a big blanket of white. And if anybody in the audience has ever been out in a snowstorm or after a snowstorm when it's really sunny, you need sunglasses because snow reflects light very, very effectively. This is called albedo. And so this white cap in the Arctic actually reflects the sun and cools off the Earth because the Earth itself is not able to absorb the heat from the sun's energy. But as you reduce the Arctic sea ice, you have less of that energy that's bounced away and more of it that's absorbed by the Earth. So the Earth actually gets warmer in that case. So lack of sea ice also means lack of albedo, which affects the climate as well.
That's right. So hopefully we've been able to convince you all of just how cool and exciting sea ice is. And I think that wraps it up for us. And now we can make an exciting announcement for next month's Rockin Pop-Up, which, Gavin, if you'll pardon the pun, it's going to be out of this world.
I will pardon the pun just this once, Graham. But I'm really excited about this. You had to twist my arm now that you're a planetary person. But I'm really excited about learning about the solar family in a 3-part series where we're talking about the planets and the terrestrial bodies in the solar system. And so part 1 being what, Graham?
The terrestrial planets, Earth and its siblings. So we're going to talk about Earth and its moon. We're going to talk about Mars, Venus, and Mercury. And it's just going to be a rockin' good time.
Sounds good, Graham. I'm looking forward to it.
I too cannot wait. I was going to make a comment that we should start calling you guys like the paleoclimatology pals instead of the Geology Gents or something, but now maybe it's the planetary pals, or we can come up with a new little nickname for you guys depending on where your interests take you. But I always love, being reminded about how geology is about so much more than just than rocks, that its forces are on play in many different ways. And that was very fascinating. Thank you. Yeah. But speaking of, rocks and identifying rocks and getting back to the basics, we did have a submission, which is always very exciting. Someone emailed us with a question about a rock that they found, and they have some thoughts. So I'm going to share the images for y'all. So here we have the rock. There are 3 pictures that they sent here. And this rock was found near Joshua Tree on BLM land. And they have a theory. They're curious if this happens to maybe be something on theme for next month. Maybe we should have saved this for February. But they thought it seemed kind of meteor-ish.
Yeah.
What do you guys see here?
Yeah. And so a couple of key things pop out here, and I see why this person has this, extraterrestrial meteoritic, hypothesis, because this has this really kind of smooth, polished surface. It looks what like meteoriticists call a fusion crust. And that's basically this sort of veneer of melted rock, this sort of glassy melted rock that forms from the heat when the meteorite enters the atmosphere. And so it's dark, it's glossy, it does look kind of like that. However, there are a couple of other aspects of meteorites that, we'll have to say that it's hard to really say this for certain just looking at images. And so Marissa's got a link that she can share on the Facebook, I believe.
Yes.
I won't speak for, I'll try not to speak for you too much, but this is a link to a really good flow chart to sort of help, do some at-home tests, because the next steps of, looking at these is, how much does it weigh? Is it magnetic? It's really helpful to crack into it and get a look inside of it. And I know that seems like like a dangerous thing to do, but that helps you start to figure out, some more of the aspects of it, what the rock inside of it looks like.
Mm-hmm. So the next time this person or anyone out there finds something that makes them think of a meteorite, they can go here and they can go through the key. And if they end up here or here, so does it have regmaglyphs, or is the inside lighter colored than the outside? Then send us some photos.
Yeah. And so Gavin and I took our best stab at sort of thinking about these things from the images we saw. So if I can share my screen for a moment. Thank you.
It's a truly beautiful specimen.
Yes.
By the way, I just want to plug the fact that is a really cool rock, and I'd love to see it in person, but it looks awesome. Go ahead.
Yeah. So whatever this rock is, whether it is of this earth or from beyond this earth, it is absolutely a glorious rock. And I would love to see, what it looks like inside. So to the finder, if they ever do sand the side of it or cut it open, would love to see what's happening in there. We're a little bit skeptical of whether it's a meteorite for a handful of reasons. Gavin, I'll let you start with just the sheer odds of meteorites on the surface.
Sure. Yeah. So I'll put it very generally. The odds are not good that you find a meteorite on the surface. I don't actually know what the exact odds are, but most of the meteorite finds on Earth are found in a few very specific places. One being the Antarctic ice, because you can imagine that it's a really good big white sheet to find very black rocks on, and they're also not actually eroded away in Antarctica as readily. Also in deserts they're found. So actually, Joshua Tree is not a horrible place, but generally it's very, very very improbable to find a meteorite on the surface. So that's a quick plug. But go ahead, Graham. Talk to me about regmaglyphs.
Yeah. So that being said, it's very improbable. Sometimes it happens. And so then, when we think we might have one, that's when we start to look for some of these physical properties. So things like the fusion crust, which we talked about. And this does have something that looks kind of like a fusion crust, but what it doesn't have that are really important are these regmaglyphs. And so these are these concave dimples on the surface. And these have to do with bits where the rock melts and splashes out. Sometimes you can have large ones that are formed as craters from these things bonking into other things before they make it to Earth. And so you can see in these images, these regmaglyphs, they're very kind of rounded and concave. They're not perfect circles. They're these sort of, they just look, it's almost like if you were to put a hair dryer at a stick of butter, the sort of thing that might form. And that's really essentially what's happening to these. They're melting out in these kind of weird ways. On this rock, the lumps are kind of in the wrong direction. And where you get those dips in there, they don't quite have that regmaglypt sort of shape to them. And so based on that, what we think is probably going on with this rock is that this has some desert varnish that formed on it. And so, Gavin, you can speak a little bit more to desert varnish.
Yeah, I actually am super interested in desert varnish, specifically as a research tool. So I'll just plug that. Graham, I also wanted to point out something that you pointed out to me before about this rock that makes me think it's not meteorite like. So in the top left image, you can really see this, where you have these fractures, these very angular fractures within the rock. That to me looks like cleavage, which is basically a rock's propensity to break along very uniform planes. And so a lot of people think about, if you look at marble, oftentimes it has the cleavage. It has a very specific cleavage, and calcite has a very rhombohedral cleavage. So these little angular geometric shapes in the rock, those scream earth rock to me and not outer space rock. But we were talking about varnish, so I'll put that aside now. So desert varnish is basically a rind that forms on rocks as they weather in the desert. And it's often really dark, like the ones we see here. And it's quite often basically oxide minerals sort of coating one side or both sides of the rock. So I think that's probably what this is. It's a desert varnish. And it'd be really cool to cut it open or break it open and see if the varnish is indeed totally covering the outside, and if the inside looks more earth rock-like versus outer space rock-like.
Yeah, but this one was certainly, this was a juicy rock for us to try and think about. And whatever it is, it's super beautiful. And though we don't think it's a meteorite, definitely go through all those steps and see where that lands you. Because it's always good to, test these in as many ways as you can to be as confident as possible.
And also, Gavin and his colleague Jessica are going to be at the museum on January 29th for our annual Laura Heacox Day event. So I'll drop a link about that in the comments shortly. But they're going to be able to ID rocks that day too. So you can bring rocks that we haven't yet to see. And then also for this person who submitted this rock, you could just bring it by and then Gavin can get a closer look at it on that day. Cool. Well, thank you so much, gents, as always, and Happy New Year. And I can't wait to see you all again next month to talk about the planets.
Happy New Year, Marisa.
Happy New Year.